Hey guys, welcome to another video lecture for Psych 370. In this one and in the next one, I'm going to be talking about some of the variables that affect classical conditioning. And so as it turns out, there are enough of those variables that I thought it best to break my coverage of them into two parts. This is part one. Now, a lot of these variables that I'm going to be discussing are also described on pages 66 through 78 of your textbook. And I will talk about most of the variables that the textbook does, but I won't be talking about all of them. So please do make sure that you read those pages of the textbook if you haven't already done so. Okay, first of all, one fairly obvious variable that influences classical conditioning is the intensity of the unconditioned stimulus. Generally speaking, the more intense the US is, the more readily the animal acquires the conditioned response. So, in other words, the more strongly the animal responds to the unconditioned stimulus, the more quickly it tends to acquire a conditioned response to stimuli that are paired with that unconditioned stimulus. So, for example, if you pair a bell with a big, juicy 12-ounce steak, then the animal that you're conditioning is probably going to start salivating to the bell much more quickly after fewer pairings than it would have if you had paired the bell with just a little morsel of food. The big steak is a more intense unconditioned stimulus than the little morsel is, right? The animal's unconditioned response to the steak is stronger than its unconditioned response to the morsel. So, using the steak as the unconditioned stimulus is going to lead to faster acquisition of a conditioned response to the bell. Or here's another example. Let's say that one of your friends has recently developed the annoying habit of punching you after he greets you. So, for example, maybe he repeatedly says, "Hey, buddy," and then he socks you in the shoulder. So, the greeting, the "Hey, buddy," is the CS, and the punch is the US. Well, if he punches you really hard, then you're probably going to start flinching in response to the greeting faster than you would have if he had only been giving you these light little taps, right? So the punch is a more intense, unconditioned stimulus than the tap is, so you'll associate the greeting with the punch more quickly than you'd associate it with the tap. So the intensity of the unconditioned stimulus matters. That is definitely a variable that affects how the process of classical conditioning is going to play out. The intensity of the conditioned stimulus matters too, and in a similar way. More intense conditioned stimuli generally lead to faster acquisition than less intense ones do. And guys, that tendency is very clear from studies on a phenomenon called overshadowing, which is yet another discovery that we can attribute to Pavlov. So, for example, in some of his studies, before his dogs were ever presented with the meat, Pavlov would present those dogs with two stimuli, such as a bright light and a faint noise, simultaneously. So, guys, those two simultaneously presented stimuli form what we call a compound stimulus. Okay, that's called a compound stimulus. And then, after repeated pairings of that compound stimulus with food, which was the unconditioned stimulus, Pavlov would test his dogs by presenting each component of the compound stimulus all by itself. So, for example, he'd present only the bright light or only the faint noise. And what he found was that the dogs would salivate to the more intense stimulus. They would salivate in response to the bright light, but they wouldn't salivate to the less intense one. They wouldn't salivate in response to the faint noise. Now, it wasn't that the noise was just too faint to work as a conditioned stimulus, because Pavlov's previous work with other dogs had shown that if he presented that faint noise all by itself, without the light, and then followed that with food, then the animals would learn to salivate in response to the noise. But when the faint noise appeared with the bright light, when he used the noise and the light together as a compound conditioned stimulus, the greater intensity of the bright light caused it to overshadow the faint noise, meaning that the faint noise did not become a conditioned stimulus for these dogs. In other words, the dogs did seem to learn an association between the bright light and the food, but they didn't seem to learn an association between the faint noise and the food. So again, we call that overshadowing, and it happens in people too. So for example, if you eat a salad with this really tangy dressing, if the taste of the dressing is just much more intense than the taste of anything else in the salad, and then later, after you've eaten the salad, you get sick, well, you're much more likely to avoid the dressing in the future than you are to avoid, say, the cucumbers that you had in the salad. So the taste of the dressing stands out more than the taste of the cucumbers does, right? It's more intense. It overshadows the taste of the cucumbers. So it's the taste of that dressing. It's that more intense stimulus that you will probably associate with the nausea. So, one variable that affects classical conditioning is the intensity of the CS or the US, with more intense stimuli generally leading to more effective conditioning than less intense stimuli do. Another important variable has to do with the timing of the CS and the US. So, what I'm going to cover next here are the different temporal relationships, we call them, that we could have between the CS and the US. Now, one such temporal relationship is known as trace conditioning. And in trace conditioning, the CS both appears and disappears before the US appears. So, for example, if the conditioned stimulus is a light and the unconditioned stimulus is an electric shock, then trace conditioning would look something like this. I'm going to show you a quick animation here to illustrate how trace conditioning would work for that example. Okay, I'll show it again. So the light, the CS, gets turned on. It remains on for a little while, and then it gets turned off before the shock, before the US is delivered. So we call this trace conditioning because the idea here is that the animal has to retain a memory. It has to retain some trace of the conditioned stimulus in memory in order for it to associate that stimulus with the later occurrence of the unconditioned stimulus. Okay, so that's called trace conditioning. Again, in trace conditioning, the CS both appears and disappears before the US appears. In another kind of temporal relationship between the CS and the US, the CS again appears before the US does, but in this one, there's some overlap between them. In other words, with this one, the CS doesn't disappear until the US is already present. So, at least for a little while, they're both present at the same time. That procedure is known as delay conditioning, and some researchers also make a distinction between short delay conditioning and long delay conditioning. So the difference between those just has to do with the amount of time that passes between the onset of the conditioned stimulus and the onset of the unconditioned stimulus. Obviously, in short delay conditioning, that interval, that amount of time, is relatively short, like this. So in short delay conditioning, there's a short delay between the onset of the CS and the onset of the US. And in long delay conditioning, the delay is longer, typically ranging anywhere from a few seconds to several minutes, like this. Now, guys, the interesting thing to me about long delay conditioning is that eventually the animal learns to stop responding to the initial onset of the conditioned stimulus, and instead it starts responding closer and closer to the onset of the unconditioned stimulus. So, for example, this graph is from a study where a 2-second long tone was paired with a puff of air to the subject's eyes. And as you can see, the subjects started to blink toward the end of that 2-second tone, meaning they increased the latency of their blinking responses, right? So that those responses would coincide more closely with the occurrence of the air puff. So, what's cool about findings like this is that they suggest that it's not just the tone itself that's serving as the conditioned stimulus. Rather, it's like a compound stimulus that includes both the tone and the passage of time. So, that's pretty interesting. if you ask me. The passage of a certain amount of time can become part of what people and animals learn to associate with the unconditioned stimulus. So it's almost like you have a sort of internal clock, so to speak, that enables you to learn not only what to expect, but also when to expect it. Okay, so trace conditioning, delay conditioning, and guys, these last two temporal relationships aren't actually used very often by learning researchers, but they are worth mentioning, so I'll talk about them together and fairly briefly. First, in what we call simultaneous conditioning, as you might expect, the CS and the US occur at the same time. So they occur simultaneously. They appear and disappear together. So to stick with our example of a light as the CS and a shock as the US, simultaneous conditioning would look something like this. So that's called simultaneous conditioning. And in what we call backward conditioning, the US actually occurs before the CS, like this. So in backward conditioning, the shock would actually occur first, and then the light, then the CS would occur. But now, like I said before, trace conditioning and delay conditioning are much more common in research on classical conditioning. Most researchers don't use simultaneous conditioning or backward conditioning in their studies. So why not? Well, because they aren't very effective. It's hard to get an animal to acquire a conditioned response to a neutral stimulus if that stimulus occurs at the same time as or after the unconditioned stimulus. By contrast, in trace conditioning and delay conditioning, the CS occurs before the US does. And like it says here, those both tend to be quite effective procedures for classical conditioning. So it's important to keep in mind that what the effective procedures have in common is that the CS precedes the US, as it does in trace conditioning and delay conditioning. And we'll come back to this point again next week when we discuss theories of classical conditioning, because one prominent theory is basically that classical conditioning is all about preparation. It says that we acquire the conditioned response because that response helps us prepare ourselves for the unconditioned stimulus. And obviously, the only way to make a preparatory response like that is if you get some sort of warning, right? Some sort of signal that the unconditioned stimulus is about to occur. And so the idea is that the conditioned stimulus is that warning. It's what allows you to predict and prepare for the unconditioned stimulus. And so it's only useful to you if it occurs before the unconditioned stimulus does. And like I said, we'll return to that idea about classical conditioning next week. For now, the main point is that the timing, and in particular the order of the CS and the US, does affect whether and how quickly a conditioned response is acquired. Next, another factor that influences classical conditioning is whether or not there is a contingency, what we call a contingency between the CS and the US. Now, guys, a contingency is sometimes defined as an if then statement, okay, as in if X occurs, then Y occurs. But a better, more precise way to define a contingency is in terms of probability. So, for example, we would say that the US is contingent upon the CS if the US is more probable, if it's more likely to occur in the presence of the CS than it is in the absence of the CS. In other words, there's a contingency between the conditioned stimulus and the unconditioned stimulus if the occurrence of the conditioned stimulus means that there is now an increased probability that the unconditioned stimulus will also occur. So, is the US more likely to occur if the CS has occurred? That's the key question here. And if the answer is yes, then you'd say that the US is contingent upon the CS. Now, a classic experiment by a psychologist named Robert Rescorla using rats as subjects demonstrated the importance of the contingency between the CS and the US in classical conditioning. So I want to take a few minutes here to tell you about that experiment. The conditioned stimulus in this experiment was a continuous 2-minute long tone. Okay. The unconditioned stimulus was electric shock, and the conditioned response that Rescorla was looking for was basically freezing in response to the tone. So if the rats learn to associate the tone with the shock, then they should eventually freeze when they hear the tone, meaning that we'd see them becoming less active overall whenever the tone was present. So, to measure that freezing response to the tone, Rescorla would present these rats with alternating 2-minute periods, one where the tone was present and one where it was absent. And he looked at how much less active the rats were during those tone on periods than they were during the tone off periods. That's how he measured this freezing response that he expected his rats to acquire as a conditioned response. So, how much suppression of their activity levels do we see when the tone is present? So, that's how Rescorla measured his dependent variable. And the independent variable in this experiment was whether or not there was a contingency in place between the tone and the shock. In other words, was the shock more likely to occur in the presence of the tone than it was in the absence of the tone? And Rescorla manipulated that variable very systematically across 9 conditions by using these combinations of probabilities that you're seeing here in this table. Now, notice that in some of these conditions, the shock was just as likely to occur when the tone was off as it was when the tone was on, right? So, for example, in condition 2 here, a rat would experience a shock during 10% of the tone on intervals, but it also got shocked during 10% of the tone off intervals. So that means that the shock was not contingent upon the tone in that condition, right? In that condition, the presence of the tone did not indicate that a shock was any more likely. And as you can see here, there was also a lack of contingency between the tone and the shock in condition 5 and in condition 9. However, in the other conditions, there was a contingency between the tone and the shock. In these other 6 conditions, shocks were at least somewhat more likely to occur in the presence of the tone than they were in the absence of the tone. In other words, in these 6 conditions, the presence of the tone did indicate that a shock was more likely than it otherwise would be. So we'd say that a contingency existed between the tone and the shock for these conditions. In these conditions, if the tone occurs, then the shock is more likely to occur compared to when the tone is absent. Now, here's a graph of Rescorla's results. Each data point here represents the average amount of suppression, the average amount of freezing, basically, that was elicited by the tone for the rats in the different conditions. The different lines represent different probabilities of getting the shock when the tone was on, so 40%, 20%, and 10%. And the different values down here on the horizontal axis represent different probabilities of getting the shock when the tone was off. So this little line over the CS, by the way, here on the bottom of the graph, that means absent, okay? So the way to read this term here is probability of the US when the CS, the tone, was absent. And guys, the thing to notice about this graph is that no matter which line we're looking at, whenever the probability of shock was the same when the tone was present versus when it was absent, we see no conditioning taking place, no acquisition of that conditioned freezing response. So these 3 points on the bottom of the graph here correspond to conditions 2, 5, and 9, the ones where shocks were equally likely during the tone on and tone off intervals. As you can see, in those conditions, the rats really didn't suppress their activity at all when they heard the tone. They basically behaved the same when the tone was present as they did when the tone was absent. However, the other 6 data points represent conditions where the shocks were more likely in the presence of the tone than they were in the absence of it. And in each of these cases, we see the animals acquiring that conditioned freezing response to the tone. And of course, that was especially true in the condition with the strongest contingency between the tone and the shock. In condition 6 here, the shocks occurred on 40% of the tone on intervals, but 0% of the tone off intervals. And in that condition, the animals almost completely suppressed their activity in the presence of the tone. So, guys, the take home message here is that what mattered in this experiment, as far as whether or not a conditioned response was acquired, was whether or not the tone, the CS, was informative, whether or not it allowed the animals to predict the occurrence of a shock. The more informative that tone was, the better a predictor of shock it was, the stronger that contingency was between the tone and the shock, the more these animals tended to change their behavior in response to the tone. So the contingency between the CS and the US. Is the US more probable when the CS is present compared to when it's absent? That is a very important variable when it comes to whether or not classical conditioning will occur. So contingency is important. And another important variable that affects classical conditioning is the degree of contiguity between the CS and the US. So, guys, when we say that two events are contiguous, we mean that they occur closely together in time. Okay. So, we'd say that the CS and the US are contiguous if the US occurs shortly after the CS does. And we typically measure the contiguity of the CS and the US by measuring what's known as the interstimulus interval, or the ISI, which refers to the amount of time that passes in between the CS and the US. So, what's the interval? What's the amount of time in between these stimuli? That's the interstimulus interval. That's the ISI. Now, with trace conditioning, where the CS and the US don't overlap, we measure the ISI as the amount of time that passes between when the CS has its offset and when the US has its onset. So in trace conditioning, we're looking at the amount of time that passes between when the CS disappears and when the US appears. And in delay conditioning, where the CS and the US do overlap, we measure the ISI as the amount of time between the onset of the CS and the onset of the US. So that's the interstimulus interval. That's the ISI. And again, we can use that as a measure of how much contiguity the CS and the US have. The ISI tells us how contiguous those stimuli are. And in general, short ISIs do work better than long ones do for classical conditioning, but there are some exceptions to that. For one thing, like I said before, simultaneous conditioning doesn't usually work. So if the interstimulus interval is so short that the CS and the US are actually simultaneous, then we tend not to see classical conditioning taking place. And in other cases, the interval between the CS and the US can actually be quite long, and classical conditioning will occur anyway. So a good example of that is a phenomenon called conditioned taste aversion, where a lot of time can pass between when you eat something and when you get sick, and you'll still tend to acquire an aversion. You'll still tend to acquire a conditioned aversion to the taste and the smell of whatever it was that you ate. Again, that's called conditioned taste aversion, and we'll come back to it and talk about it in more detail in a couple of weeks. But anyway, the point for now is that the importance of this contiguity variable does depend on a number of other factors too, with the ideal interstimulus interval being affected by things like what the CS and the US are, what kind of response the animal is learning, and whether you're using trace conditioning or delay conditioning. So for more information about those factors, I'll just refer you to the textbook's coverage of them, which you can find on pages 69 through 71. Okay, that's a good place to stop this video lecture. So please let me know if you have any questions about this stuff. And please also make sure that you check out the next video lecture where I'll be continuing this discussion of variables that affect classical conditioning. Okay, take care.